we are moving on from looking at the mathematical model to how it's solved by the tool using a numerical solution procedure. So we're going to look at the second step of the pre-analysis, the numerical solution procedure. And we'll focus on what's the strategy used and what are the errors introduced by that strategy. And to talk about the numerical solution strategy, I'll go back to ideas we looked at in the big ideas in CFD. So we take our domain and we discretize it into cells, and we determine the two components of velocity and pressure only at the centers of the cells. So I've marked out 4 cell centers here, pardon my chicken scratch. And the tool will go from the boundary value problem, the mathematical model that we saw, to a system of algebraic equations in cell center values. And these algebraic equations will relate, neighboring values of velocity and pressure at the neighboring cell centers. And the system of algebraic equations is derived by performing a control volume balance for each cell, as we've seen before. And once it has a system of algebraic equations, it'll invert it and determine the cell center values of the velocity and pressure. And everything else is extracted from those cell center values. So for instance, if you wanted to know the pressure field, pressure anywhere, you would interpolate between the cell center values. Similarly for velocity, the wall shear, you have to interpolate and differentiate to get the wall shear. And that whole process is, as we've talked about, post-processing. And in this process, there are 2 errors introduced, discretization error and linearization error. So let's do a quick review of those errors. And again, going back to ideas we saw before. The tool will derive, in our case, ANSYS Fluent will derive the algebraic equations relating cell center values not from the differential form, but from the integral form. Okay? These 2 forms are equivalent. There is no error introduced in going from the differential form to the integral form. But in going from the integral form to the set of algebraic equations, an error is introduced, the discretization error, which can be reduced by, by refining the mesh. The algebraic equations are nonlinear, so the tool will linearize it about guess values and get linearized algebraic equations. And in the process, a linearization error is introduced, which is reduced by solving iteratively. So the tool will solve iteratively, updating the guess after each iteration. And when the imbalances of mass and momentum fall below a tolerance, you can ask it to stop the iterations. And when the iterations have converged, the linearization is below a tolerance, and we have an approximate solution to the governing equations and boundary conditions. And that approximate solution has a linearization error, which is below a tolerance, and it also has a discretization error, which depends on the mesh that you provided to the solver.